All right, this is Calc AB Notes 2, page 2, the second video. We're just doing a lot of chain rule problems, trying to get used to it. So what I've been doing is I've been kind of like highlighting what I think is the most outer function and working my way to the inner. So I look at this next problem and I see we're doing cotan of something, right? But what are we doing the cotan of? We're doing the cotan of 8, or give me my, here we go. Cotan of 8x, right? So I do these problems by kind of thinking them through. So I think to myself, I'm going to find dy dx. All right, the derivative of cotan of something is the negative of the cosecant squared of that thing, and that thing is 8x, and then times the derivative of that thing. The derivative of 8x is 8. And that would be it. I'd be done. You could rewrite it, but I'm going to kind of highlight. So first, it's the derivative of that outer function with the inner function kind of plugged in, and then times the derivative of the inner function. So that's where all of that comes from. You could also do it, and I think I might stop doing this because I don't really do this that often, but I find that like when you're first starting, it can be helpful for some people. So it's y is the cotangent of u, and then u is equal to 8x, and then to find dy dx, it'll be dy du times du dx. And then we just find those things. So dy dx will equal dy du, the derivative cotangent of something is negative cosecant squared of that thing, and then times du dx is 8. And so then you would substitute in, and when you substitute in, you end up right back there. So it's the exact same process. It's a little clearer, I think, when you do it this way initially, but you want to kind of move beyond that so that eventually you're doing them more fluidly, and just you kind of want to get to the point where you can look at it and just take the derivative. I mean, that's our goal, is to get to the point where we're just looking at it and finding the derivative. So here, so ultimately you're going to take the cosecant of something. And then the question is, what are you taking the cosecant of? Well, you're taking the cosecant of sine of something. So this derivative, what is, so dy dx, what is the derivative of cosecant of something? It is negative cosecant of that thing, cotan, I'm going so slowly that I forgot the derivative of cosecant. Negative cosecant cotan, so negative cosecant of that thing, cotan of that thing, and that thing is sine of x, and then times the derivative of that thing, which is cosine of x. And you know, this doesn't simplify any more than this. It'd be nice if it did, but like they're all normal trig functions. There's no like inverses or anything in there, so it's not going to simplify more. So the first part is coming from the derivative of cosecant of something, and the second part is from the derivative of the thing, and the thing is sine, so the derivative is cosine. I'm not going to do the other version on that because it just takes a lot of space. And also, I mean, you can do it. So do it on your own, see if you get it. It should match up perfectly. I'll do the same. You know what I'll do? I'll do the other version here. I'll say that y is equal to the tan of u. U is equal to the square, oh, it's a long square root. Square root of x and then plus 2. 2 plus radical x is safer because you'll never think that that 2 is inside the radical, whereas the other way around, you might accidentally think that. Whatever, it's up to you. So dy dx is going to be dy du times du dx. I find it very useful to write this part out when I'm doing them using this form of the chain rule. So the derivative of, so dy du, the derivative of tangent of something is secant squared of that thing, u, and then times the derivative of that thing. The derivative of square root of x plus 2 is 1/2 x to the negative 1/2. So we get this, and then finally we'd want to write dy dx as a function of x, not a function of u and x, but u is equal to square root of x plus 2, so we can do it. So secant squared square root of x plus 2, and then times, I don't, like, there are ways you can simplify this, but I don't really think it's going to look all that much better. So let me like trace, let's derivative trace here, right? We're doing the tangent of something. So y is equal to tan of u. There'll be a dy du. This comes from that. And then that comes from that also. So this comes from that. Okay, so that's tracing that through. And then we got this, our inner function here, which we called u. So we needed the u dx, which is this, which gave us this. And there you go. You can like trace your way all the way through it, which I think is super useful. Let's take a look at these. So this is the next most. I really feel like the chain rule, the key to mastering it is to really start with some trig functions, because for whatever reason, when you're working with trig functions, it's very clear that you're going to need the chain rule. Now, these are problems that we've been not wanting to do because we know we can expand it and just power rule each thing, but like that's a lot of work. So the chain rule is going to let us do this in a more efficient way. So let's see if we can do it. So I see, I'll keep highlighting, but you want to move away from that if you can. I see like something to the fifth, and then it's like, what to the fifth? Well, this thing to the fifth, right? So the derivative, dy dx, is going to be, the derivative of something to the fifth is 5 times that thing to the fourth. So 5 times that thing, which is 3x minus 2, to the fourth, times the derivative of that thing. The derivative of that thing is 3. So we'll say dy dx is 15, 3x minus 2 to the fourth. You could do the thing where you say, I'm not going to carry it all the way through, but y is equal to u to the fifth, u is equal to 3x minus 2. dy dx is dy du times du dx, and you go for it. You're going to end up in the same place. So this is our final answer. Let's try the next one. So dy dx. So I see a big outer function. The outer function here is something to the seventh. Something to the seventh. And then the question is, what is being raised to the seventh? Well, it's this thing. So that's our inner function. So here we go. The derivative of something to the seventh is 7 times that thing to the sixth times the derivative of that thing. What's the derivative of 19 minus 3x to the fourth? It's negative 12x cubed. So minus 12x cubed. Ooh, tense moment. Got to multiply 7 and 12. Negative 84x cubed. Quantity 19 minus 3x to the fourth to the sixth. That's my final answer. So they're not that bad. You definitely have to get used to it, but like it becomes second nature. You use it all the time in other problems. That's the key thing to realize. Like you are going to be using this all the time. Like it's not going to be a problem where it says use the chain rule to find the derivative. It's just going to say find the derivative, and you have to look at it and realize like, oh, it's composition. I'm going to use the chain rule. Same as it doesn't say use the product rule, use the quotient rule. Just find dy dx or y prime or f prime, whatever. That's what you got to know. So here we go. Dy dx. So it's going to be 4 times this thing to the third, and then times the derivative of that thing, which is, it's really important to put this in parentheses though, so that everything gets distributed the way it should. And then I would probably rewrite this for like almost no reason. Usually you just put the linear thing first. I don't really know. I don't know if that's necessarily a rule, but you know, so that it looks like what other people normally do. I think we should probably do it. So what I'm gonna do, I'm gonna cut this video here, come back in the next one, finish this page, and then keep going. So hopefully you are finding this useful, and I'll see you in the next one.